Now this time, let us see a couple of problems where we have to apply Kirchhoff's rules. Here is one. They give us this circuit, and our task is to find the unknown currents. They show us some directions of currents, but we know that even if we are not sure about the directions of the current, it doesn't matter, because once we do the calculations and we find their values, if we find negative values, means that we had chosen the opposite direction. So anyway, so here is our circuit. We have, how many unknown currents are there? We have here, we see I1 in a clockwise direction. Then in this middle branch, we see this current I2. And at the bottom branch, we see the current I3 in a counterclockwise direction. So we have three currents, three unknowns. We need three equations, because then we can solve them as simultaneous equations. In other words, we can solve for as many unknowns as we have equations. So here we need three equations. All right. The easiest equations we can write is when we apply the first rule, the junction rule. Let's take point A, for example. Let's start with point A and apply there the junction rule, the first rule, where we have all the currents in must equal to all the currents out of this junction. So, okay, let's see what we have here. I2 is in, I1 and I3 are out. Okay, so I2, which is the in, must equal to the sum of the I1 plus I3. So this is our first equation. We need another two equations. Okay, I mean, if we apply for junction C, it's the same equation, we get nothing new. So let us go to the second, let's apply the second rule of Kirchhoff's rules, the loop rule. So let's apply it on the, in this loop, the top loop, A, B, C. Okay, so let's apply to this loop. All right, let us start from somewhere. Let us start from this EMF. Now, what does this rule say? It says that the sum of all the M's in a loop, in a closed loop, must equal to the sum of all the potential differences. All right, so let us start from here. Let's start from the 1,5. I'm not going to write units. Units are all SI. So if we start from the 1,5 EMF and follow this current, let's follow this in this direction. Let's follow this loop in this direction. Then we meet this EMF of 3 volts, but be careful now how we meet it. It's we have to subtract this, because look at the current, how it meets this battery, whatever this is. So this has to be subtracted, -3. You see, why do I subtract this? Because we started from the 1,5 volt EMF. Look at this, the current has a direction from the positive, that's the positive terminal, that's the negative. It seems to start from the positive terminal. But in this case, when we meet the other EMF of 3 volts, look at this current. It's like goes into the positive terminal. That is why we need to take this as negative with the opposite polarity. Okay, so these are the sums of the EMFs. There's no other EMF in this loop. Now let's take the sums of the potential differences across the resistors. So here we have one resistor, 20 ohms, with the current I1. This is I1 in this direction, so this will be positive. So 20 times I1. Okay, and we continue and we meet the 15 ohms. The current in the 50 ohm resistor is I2. So we add this. So 15 times I2, and that's it. So this is the second equation for this loop. We finished, we have no other EMFs or potential differences in this loop. Let's go to another loop now, because we need the third equation. Let's go to this bottom loop, A, C, D. A, C, D. Let's see what we meet here. Let's start again with the sum of the EMFs. Let's start again from this 1,5 volts. So that will be a positive sign here, 1,5. 1,5, and we continue following this direction of the current, and we meet the 6 volts. But again, look at this. The current kind of like enters the positive terminal, so we have to subtract this EMF minus 6, like the same case as in the previous loop. And this sum of the EMFs must equal now with the sum of all the potential differences that we meet. So the first one is 10, this 10 ohms resistor times the current I3, it's a plus, 10 times I3, and plus, we continue, plus I2 times 15 ohms. So 15 times I2. And this is our third equation. So now we have finished the physics. We have the 3 equations that we need, and we can solve them as simultaneous equations. We can afford to solve to find up to 3 unknowns, which are our 3 currents. The unknowns are I2, I1, I3. Here it has an I1 and an I2. The last equation has the I3 and the I2. I must say now that this from now on is algebra. And yeah, it can take some time to solve these 3 equations, but let's try. I have done some calculations here, and I hope my calculations are correct, but we have some answers here. Let's see if we can find the same things. Look at these answers. The I2 has a negative value, and the I3 has a negative value as well, which means that here in our diagrams, the I2 and the I3 correctly would be in the opposite direction. But let's see if we can find some similar values if we solve it. Okay, so what do we need to do? All right, I2, let's say that we replace the I2 in both equations with I1 plus I3 from the first equation. Okay. Do I have enough space now? With my big handwriting. Let me find some clean space here. Okay, let me write again the equations. What was the first one? I2 was I2 is I1 plus I3. The next equation, I hope I write it the same way, was minus, sorry, it was 1,5 minus 3. That was 20, what? 20 I1 plus 15 I2. Is this correct? Let me see. 20 I1 plus 15 I2. Okay. And the next one is 1,5 minus 6. 1,5 minus 6 equals to 10 I3 plus 15 I2. I have them here in my scribbling books. I hope it's the same. 10 I3 and 15 I2. Okay, good. All right. So here are our equations. All right. So, all right. We said we replace the I2 in both those equations so that we are left with only I1 and I3, 2 unknowns in other words, so we can solve it with these 2 equations. All right. So 1,5 minus 3 is minus 1,5 is 20 I1 plus 15. So instead of I2, I'm going to write I1 plus I3. And if we do the calculations here, that would be plus 15 I1 plus 15 I3. And that would be altogether 20 20 plus 15, I1 is 35. 35 I1 plus 15 I3. Okay, that is equal to minus 1,5. Okay, from the second equation, 15 minus 6 is minus 4,4. And I3. So here replace again the I2 from there. So 10 I3 plus 15 I1 plus I3. And this is 10 I3 plus 15 I1 plus 15 I3. Oh, 15 I3. So 10 plus 15 I3 is 25 I3 plus 15 I1. And this is equal to minus 4,4. So there we have one equation. And this other equation, which is, what is this? This is equal to minus 1,5. So you see now I have two equations with two unknowns. So I have reduced my equations. Anyway, if we do the calculations, let's see now. We can solve for I1, for example, one of it, both of them. So let's call this 1 and this 2. So for 1, if I solve for I1, this will be equal to minus 1,5 minus 15 I3 divided by 35. And from the second one, if I solve for I1 again, yep, so that will be minus 4,4 minus 4,4 minus 25 I3 divided by this 15. So you see these now are equal, which means if I equate those two, I can solve for I3 and so on. Now, let us not spend a lot of time in mathematics. From here, I find that I3, what do I find? I find that I3 is minus 0,202 amperes. Let's see, according to these answers that I have. Okay, let me see what else I find here. So that I also find then if I replace the I3 in either of these equations, I find the other current, which is what? I1. The I1, I find that it is 0,043 amperes. And let's see, which are quite similar to the answers that we have here. For example, I3 here, I found 0,202 amperes. I don't know what's the little difference here. And for I1, I found it 0,043 amperes. Anyway, there we have round up some different numbers. So nevertheless, along this path, our solution, our answers are quite acceptable. And the I2, according to, if I follow my values, I find that I2 is minus 0,159 amperes. Of course, now let's look at this. We have from one or two significant figures. So if I change them into significant figures here, I should take one significant figure really. Whew. But nevertheless, these are the answers that they give us. So let's say let's change them to 0,2 here amperes, and this can become 0,16, well, about 0,2 as well amperes if I round it up. And this, that's too much to round up, 0,04. Let's leave it like that. So these are the values of currents, and you see I2, where is I2? I2 is this one. Because we found the negative value means actually the actual direction of the current I2 is in the opposite direction that from what we had initially or given initially. And what is it? The I3 is also in the opposite direction. So the I3 is not from left to right here, it's in the opposite direction. That would be the direction of I3, and it has this value here. So nevertheless, the idea for us to understand the physics of it, it's just that we need to find the equations, the proper equations, and then we can apply your maths knowledge to solve for the unknowns using the way we solve simultaneous equations. Okay, so roughly this is how we solve it. Now, don't you worry, because it seems that in the exams, in past exam paper questions, you don't have to do all these calculations. In fact, I found a past exam paper where they just ask you to find the equations. They don't ask you to solve them as well. Where is this? Let me find it. Is it this one? Yeah, this one. Look at this. This is from 2017, October, November 2017. This exam paper. And let's see what it says. It's 3 cells of electromotive forces, E1, E2, and E3, are connected into a circuit as shown in the figure 5.1. The circuit contains resistors of resistances R1, R2, and R3, and R4. The currents in the different parts are I1, I2, and I3. And they show us where the resistors are, and they also show us some directions of currents. Okay, so we see where the EMFs are and the directions, and use Kirchhoff's laws to state an equation relating. So they tell us actually which equations and what must it relate. So first, they want us to write an equation that relates the currents I1, I2, and I3. In other words, we have to apply the first rule of Kirchhoff, the junction rule. We can take any point where the 3 currents meet, like W or Y. It should be the same equation, really. So for W, let's take the first rule for the point for the junction W. Okay, here is the I2, it comes into the junction, then we have I1, so here would be I1, like this, and I3 seems to go out of this junction, according to the currents that they have marked here already. So this is the I3, and this is the I1 and the I2. Okay, so junction rule, currents in equal to the sum of the currents out. So I1 and I2 seem to go into the junction. Let's put them together then. The sum of I1 plus I2, which are the in currents, must equal to the sum of the out currents, which is just I3 here. So this is the one equation that relates those 3 currents. I2 plus I1 equals to I3. Okay, so this is our first answer. We have one equation. Now, we need the diagram. Now, we need to link, to relate E1, E3. Okay, E1, where is E1? Okay, E1 and E3, all right? So this and this, and the resistors R1, R3, R4. R1, R3, R4. In other words, they want us to take the second, to apply the second Kirchhoff's rule, the loop rule, for this outer loop. They don't say outer loop, they say R3, R4, R1, and E1, and E3, and all this. Okay. In the loop, here it is, W, X, Y, Z, Y. All right. So, okay, so this loop, let's start from one of the EMFs. The second, the loop rule of Kirchhoff says that the sum of all the EMFs must equal the sum of all the potential differences that we meet as we go around the loop. Okay, let's start from E3. Okay, let's begin from E3. So E3, now what if we go all around, what else do we meet? There is another EMF that we meet. And how do we meet it? Be careful now. The current leaves here the positive M. Now, how do we meet this is minus, this is plus. The current seems to be in the correct direction as it was in this EMF, in this battery. So this we added. So this is plus E1. Okay, so E3 plus E1, and that's it, finished. Now we go to the potential differences. The sum of the potential differences must equal this sum. Okay, so what potential difference we meet? This we meet resistor R4 with a current I3 there. So this is a positive R4 times I3. And then we move along and we meet resistor R1 with a current I1. So we add it as well. So R1 times I1. And what else? Oh, here we meet another one. We meet the R3. R3 with current I3. It's also, we need to add it. R3 times I3. And there's our equation. These are the three potential differences across the three resistors that we met. They're all positive values. Well, according to this direction of currents that we have. So here is this equation that relates all these items that they ask, which is the outer loop. Second equation. Okay, we need one more equation. And the reason they ask us to write these three equations, including this that we're going to write now, is because we have three unknowns, the three currents, usually. Oh, we actually don't know anything here. All right, no problem. Usually in problems, when they give us arithmetic numerical values, usually they will ask us to find the three currents, or number of currents, or something else. But anyway, what loop now must we take? Let's see what Y, Z, W, Y. Where's Y, Z, W, Y? Ah, this is the bottom right loop. All right. So this loop, we have E2 and E1 there. Let's see. Let's start from the E1. Here is a current in the E1. We need to have to stick to the directions that we are given. So this is current I1. All right. So let's start from here. E1, let's write E1, which is the first one. Then let's follow the direction of this current, and then we move into this branch and we see we meet this E2, but now the current in this section, look at this, which is the I2, is in the opposite direction that the one that we are following here. So we have to subtract this. So minus E2. So minus E2. So okay, we have finished with all the EMFs that we need. Now this must be equal to the sum of all the potential differences that we meet. Okay, now what do we have here? The first potential difference is this I1, R1, okay. So R1 times I1, and as we move along and we follow this direction, what is this? Clockwise direction. Eh? So what we meet now the R2, but look at the current in the I2 is in the opposite direction that the one we follow. So this, we have to subtract it. So this will be minus R2 times I2. Okay, and that's it, nothing else. So this is our third equation. So here are the three equations that they have asked us to write down. And here we stop because they do not tell us to find anything. Actually, we are not given any numerical values. We just need to check whether we can write the equations correctly with the correct signs as we apply the two Kirchhoff's rules. And in fact, this is the physics, as we say. This is a physics exam. It's not a matter of spending all our time writing, solving equations and simultaneous equations that take some time. Eh? So this is what we do here. Anything else? This is This is the only, there's no other question on this problem. There's a different problem than starting. All right. So hopefully this gives us an idea of how to apply Kirchhoff's rules in more complex circuits. Okay. All right. So next week we can solve perhaps some more. Perhaps we can start solving problems that involve internal resistances of batteries.